And this electric field has, well, let's think about the pattern here. Now, we have it hooked up to a galvanometer in order to actually see a current, but essentially what we have, if we were just looking at one turn, is a loop of wire. Okay, so here's a metal wire. And during this brief time, in both of these cases, either with the bar magnet or with the power supply, during this brief time there was a changing magnetic field. We saw a conventional current. Now, let's say conventional current is going that way around the loop. So we said that there's got to be an electric field to drive that conventional current. How does the electric field point? What's the pattern? It's got to be pointing in a circle, right? And we said that the electric field has got to point in relation to the conventional current. Electric field is pointing how? Same direction. Same direction. So there's got to be an electric field in this metal wire that is in this sort of curly pattern. In fact, the book calls it a curly electric field. To distinguish it from the electric fields we've been dealing with before, the previous cases we've been looking at electric fields that have been created by charges. Electric fields created by charges can't have this pattern because the round-trip potential difference, we said, has got to be equal to 0. But in this case, if we choose a path integral going around this circular path, we're going to get a non-zero E dot dl, right? Because every single piece of that path, that E dot dl dot product is going to give us some non-zero contribution, or some positive contribution if we're going in the counterclockwise direction, just like we did with Ampere's law. So it turns out this isn't equal to 0 anymore, and sometimes this is called labeled ENC, meaning it's a non-Coulomb electric field. Okay? So it's different. This is a different thing. We've not encountered this phenomenon before. It's an electric field not created by charges, but associated with a changing magnetic field. And in fact, the way, let me just sort of give you the equation, and then we'll eventually pick it apart. It's associated with a change, in fact, a time derivative. And it turns out, to make things work right, it's got to be a negative sign here. But it's a negative time derivative of a magnetic flux through the area bound by this loop. So a magnetic flux, remember, is B dot n hat dA. Okay? So this thing is called Faraday's law. What do we have over here? We have a electric field over a round-trip path, okay? So in other words, a non-Coulomb electric field. So you can think of it as a non-Coulomb force per unit charge, right? Remember, electric fields we can say are, you can take the electric force and divide it by the charge. It's one way to define an electric field. And a non-Coulomb force per unit charge times the distance, well, force times the distance is what? Work, right? So a non-Coulomb work per unit charge is also called what? We gave a special name for that. Non-Coulomb work per unit charge. For instance, in a battery is called what? Not potential energy, but it's related to potential energy because the potential energy is coming from the electric field, or the Coulomb electric field, right? But in a battery, remember we said we have to do work against that electric field in order to get the charges to move the opposite directions. So if you have a positive and negative terminal, the electric field is pointing that way. The force on the mobile electrons is that way due to the electric field. And so you have to do work in that direction by a non-Coulomb force to get them to move in that direction. And that, someone said it, that non-Coulomb work per unit charge is called what? EMF. That's an EMF. So another way that Faraday's law is sometimes written is that this is an EMF equal to a negative time rate of change. And as I said, this thing is a magnetic field through an area or a magnetic flux. So we can also write it this way. This is an EMF because we have a non-Coulomb field doing work over a distance, okay, or exerting a force over a distance. Okay. We need to go through some steps in order to figure out how to get the direction of these electric fields that are created by changing magnetic fields. And there's a procedure we have to go through. So we're going to spend some time just talking about how to get the direction before we do any calculation on this. So direction of this non-Coulomb electric field. And there's just a procedure you have to go through, and you just kind of have to go through the steps each time in order to get this right. And the first step is you want to draw the initial magnetic field at the location you're interested in. So for example, inside this loop, if we were trying to find the electric field around this loop. Second step is draw the final magnetic field. Okay, if the magnetic field's changing, we're drawing it at some initial time, then waiting some short amount of time, and then drawing the new magnetic field after a short time later. Step 3 is draw the change in magnetic field, delta B, which is B final minus B initial. Okay. And then there's yet another right-hand rule. Sorry, but we just can't avoid it. And the way it works is this. Point your thumb of right hand in the direction of negative delta B over delta T. Okay? And this negative sign is showing up here, so that's why we need this negative dB dt direction. And then the fingers of your right hand curl around in the direction of the non-Coulomb electric field. Okay? This isn't the only way to get this direction, but it's really the most straightforward way. And if you just stick to the steps, you should be able to get it right every time. Okay? So we're going to go through some examples here. And let's take a look at a question or two. Let's see. So the first thing we want to do is just remind ourselves how to find changes in vector quantities. And so let's just think about finding delta B. Here is a bar magnet. South pole is closer to the origin than the North Pole. Okay, so arranged this way. And we're at time t1, it's here, and then we're moving it closer. So at time t2, the bar magnet's closer to the origin than it was earlier. What's the direction of delta B? Okay, so we just want to figure out what's the direction of the change in magnetic field. Reminder, the first thing you should do is draw the initial magnetic field. Next thing you should do is draw the final magnetic field. Think about what changes between the two. Then you should be able to figure out the direction of that delta B vector. And we're all over the map. Okay, so drawing pictures is really the only way you can do this. And if you're trying to do it in your head, you're probably going to make mistakes. So let's just draw the picture. You have, and we're looking for the delta B at the origin, right? So here's our bar magnet. The first thing we have to think about is what's the direction of the magnetic field initially? It's pointing what direction? Down. Okay. We know that near the South Pole, the magnetic field is pointing down. So that's B initial. Okay. And, well, let me get rid of this. I move the bar magnet closer. What happens to the magnetic field? It gets larger, right? So B final is pointing down, but I should draw the vector bigger. Okay. So there's B final. What's the direction of delta B? Down. It's got to be down, negative y direction, right? If I have a vector pointing downward and I want to make it bigger, I have to add to it a downward vector, right? So that's delta B. And you can do this graphically in a number of different ways, but just in any vector quantity, it doesn't matter if it's a magnetic field or not, you can always draw the vectors tail to tail, right? And then the delta B points from the head or the tip of the initial to the tip of the final, right? Or you can think about adding vectors graphically. If I add B initial head to tail with delta B, I get back B final, right? You can think of it as B final is equal to B initial plus delta B, right? So we're just adding two vectors graphically, B initial and delta B, giving us a larger B final, right? Is this okay? Okay, this is kind of basic vector stuff, right? So this might be a review, but something you got to be able to do. Let's try another one. Now you can kind of get the idea. Same thing, similar sort of thing. We have the North Pole closer to the origin. Now we're moving the bar magnet farther away. And be careful here of the sign because I'm asking for negative delta B over delta T. Okay, so the steps are first find B initial, find B final, find the change, then find the negative change divided by a short amount of time. So the vector should be we're just dividing by a positive number there. Okay, a bit more agreement this time. Answer number 3, positive y direction. I believe that is correct. The North Pole is getting farther away, right? So we have the initial magnetic field pointing. B points how? Up. B points up. So that's B initial. If I move the magnet farther away, B final is up, but smaller. Thank you. So there's B final. Delta B is down. Delta B is down, but negative delta B is therefore up. Okay? So that's delta B. Negative dB dt, or negative delta B over delta T, is pointing up. Okay? So what we'll do next time is that now that we know how to figure out these changes in the magnetic field and the negative change in the magnetic field, we can then apply the last step, which is figuring out what the direction of the non-Coulomb electric field is in a situation like we demonstrated earlier.